Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at setting up and solving a more challenging, complex projectile motion problem. And specifically, the problem we will be looking at is number 5 on your review for test 2. I'm going to go ahead and read you the problem. And if you want access to the problem directly, remember your review is posted on Canvas along with the key for the problems that we're going to be working through. So here, our problem says this. As we read, I will go ahead and make a picture so we can see visually what's happening in our scenario. Problem 5. As commander in the medieval army, let's go, you are laying siege to an enemy castle. To have an appropriate method of attack, you and your troops decide to attack the castle from on top of a cliff some distance away. Okay, so problem number 5. We are attacking an enemy castle. So we are on a cliff, and we've got the castle some distance away. Looks a little bit more like a cake, but that's okay. And you all are familiar with the limitations in my visual drawing skills. So, next it says this. Your point of attack will be directly on the edge of the cliff. So right here is where we will launch from, which is located 50 meters above the level of the castle. So it says 50 meters above, which means, that's not a very good 5. That will bother me, so I will go ahead and adjust it. 50 meters above, not 50 meters in front of, above the level of the castle. If you are launching projectiles at an angle of 25 degrees above the horizontal with a velocity of 45 meters per second, so that means we're launching at 45 meters per second at an angle of 25 degrees above the horizontal, which just means above the main level of the ground. How far away is the castle if your projectile hits the castle? So we're looking for how far away our castle would be. How far in the world of physics means solve for delta x. How far away is the castle if our projectile does hit the castle? And it might not necessarily be exactly how its trajectory looks, but approximately like what you see. So, with any kinematics or projectile motion problem, we want to start by drawing a picture of our scenario. Now that we have that picture, we can go ahead and list out our variables. So, here we go. Delta x, how far our projectile travels, we don't know. I'm going to go ahead and put a box around that variable so we know this is what we want to try and find. Initial velocity in the x direction, we also don't know yet. Won't put question marks by all of these. Final velocity in the x direction, acceleration in the x, and time. I'll go ahead and fill in acceleration. We will assume to be 0 because for our scenario, we're going to ignore air resistance. In the y direction, delta y, initial velocity in the y, final velocity in the y, acceleration in the y, and time. We will assume we are on the Earth, so negative 9.81 meters per second squared. And we know that value because that is the constant for acceleration due to gravity. So looking back at our picture, I have two numbers primarily that we care about, 50 meters and a velocity of 45 meters per second. We will use the angle, but it won't really go directly into our list of variables. So coming back, our delta y here is going to be negative 50 meters. The reason that value is negative is because our ending height is on the ground. Our starting height is 50 meters above the ground, which means our object in total is displaced by negative 50 meters. And its ending height is lower than its beginning height. We also have a velocity of 45 meters per second, but it's at an angle, which means we can't just take that value and throw it into one of our variables, velocity in the x or velocity in the y, because it's kind of in both directions, which means we have to break it down. So I'm going to scroll down here just a little bit, and I'm going to redraw the picture for our velocity vector, 45 meters per second at an angle of 25 degrees. So what I will do here is I will draw in the components of my velocity initially. Initial velocity in the x is equal to, you don't know yet, and initial velocity in the y is equal to also something we don't know yet. Pardon some of the noise, they're doing some work on the building, and that can be a little distracting, so I'm sorry if that is causing you some issues here. Now, we are going to use a trig function here. I'm just going to write them out so I remember. So, ka, toa. So let's start with the x direction, because it's right here. It is adjacent to my angle, and we know the hypotenuse, so we can use a cosine function here. That would look like, scroll back up, sorry. Cosine of our angle, 25 degrees, is equal to our x component, because it is the adjacent component, over our hypotenuse, 45 meters per second. And then we will multiply by 45 on both sides of our equation to get our variable by itself that we are looking for. So 45 over 45, those will cancel out. And I will have a value, initial velocity in the x direction, equal to 45 cosine of 25 degrees. Now we can plug this value in, making sure we're in degree mode. 45 cosine 25 degrees. That would be 40.8 meters per second. Initial velocity in the x, 40.8. Now again, it's not our final answer, it's just one part of getting there. So next, we can solve for our initial velocity in the y direction. But because that y direction is opposite or directly across from my angle, I'm going to have to use a different function. Here, I would go ahead and use sine. It relates the opposite side to the hypotenuse side. So I'll write that out here. Something like sine of our angle, 25 degrees, is equal to, yes, 45, oh gosh, no, my apologies. Initial velocity in the y, which is opposite, over 45, which is our hypotenuse. Almost made a mistake there. So we'll multiply by 45 in the numerator on both sides of our equation. 45 divided by 45, those values will cancel out. We'll now have an expression for initial velocity in the y that looks like this. 45 sine of 25 degrees. We'll plug this value in, similar to what we did just a moment ago. We get 19.01 meters per second. So now we have our initial velocities. Wait, 19.01. We have our initial velocities in the x and the y. It's a very important step. We can't just take that 45 and assume it's all in one direction. And we specifically can't do that because we're told it's not in one direction. It's at an angle. We've got to watch out for those things. So now we'll come back to, here we go. We'll come back to our list of variables. We'll plug these in. Initial velocity in the x was 40.8. Which again, because our acceleration is 0 in the x direction, that means we know both of our velocities in the x. All that really tells us is we don't speed up or slow down in the x direction. In reality, we actually would because of the effects of air resistance. Here we're going to assume we don't. In the y direction, our initial velocity was 19.01 meters per second. Okay, so once we're here, and again, we're trying to find delta x, which means we will need a time value in order to get there. All these variables tell us right now is we're moving at 40.8 meters per second, and we keep moving at 40.8 meters per second. It's not enough to really get us the answer we're looking for. So we want to find time, which means we don't know v1, so we might need to use equation number 2. So we can list out equation number 2 for the y direction, which looks like this. Delta y is equal to initial velocity in the y direction times time plus 1/2 acceleration in the y direction times t squared. So we'll plug in what we know. Delta y is negative 50 meters. Initial velocity in the y was 19.01 meters per second plus 1/2 times t plus 1/2 times negative 9.81 meters per second squared times t squared. Now we'll multiply through by anything we can. Negative 50 is by itself, so it will stay as negative 50. 19.01t will stay as 19.01t. 1/2 times negative 9.81. This becomes negative 4.905 times t squared. Now, as you'll notice, this is something we also discussed in class. Okay? This equation is going to be something we need to use the quadratic formula in order to solve, because we have a polynomial. Okay? It's t squared, t, and then something without t. So what I can do here is I can move everything to one side of my equation. Let's say I move the 50 over, because we already have two values on the right-hand side. I can rewrite my expression like this. Negative 4.905 t squared plus 19.01t plus 50 is equal to 0. Now in class, we talked about, well, if we have a scenario like this with a polynomial, then we can use the quadratic formula. This value in front of t squared, we would call a. This value in front of t, we would call b. And this value by itself, we would call c. Now in class, we didn't actually go through and solve it this way, but we're going to do it here just so you can see that we could do it. So our equation for the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Now it's a bit of a lengthy equation. I'm going to, let's see if it doesn't want to stay together there. I'll move it over here just so we can see. This by definition is the quadratic formula. We could use this to solve for x. Here that would be a time value. So it would look something like this. Negative b, so negative 19.01 plus or minus the square root, probably run out of space here, 19.01 squared minus 4 times a, which is negative 4.905 times 50. And I'm just going to go ahead and work below this because I know I'm going to run out of space. So here we go. X equals negative b, so negative 19.01. Scroll up so we can see it. Plus or minus the square root of b squared, so 19.01 squared minus 4 times a, which is negative 4.905 times 50, all divided by, well, 2 times a, which is negative 4.905. Now again, we're not required to do this, but we can solve it this way if we would like to. So I'm going to plug in everything under my radical here. 19.01 squared and 4 times negative 4.905 times 50. So I'm going to get here for 19.01 squared. I'm just going to plug this value in now. This is actually going to become 361.38 minus, you have to be careful here, it is going to be minus a negative 981. So remember, subtract a negative, that will turn our value into a positive. So now we'll add 361.38 plus 981. I'm going to get a value of 1342.38. So 1342.38. Now again, if I were you, I would be writing these things down. Hey, here to keep things a little bit more simplified, I'm just going to erase and rewrite. So now we can take a square root. That would be 36.63. So we'll get rid of our square root. 36.63. And now we can simplify down to solve for the value that we're looking for, t. Now, if I notice here, this is a plus or minus, which means there are two things I can do. One, I can take negative 19.01 minus 36.63, or I can take negative 19.01 plus 19.63. Oh, excuse me, I'm sorry. Negative 19.01 plus 36.63. Looks like it's a negative there. There we go. Now, which one are we going to go with? Well, oftentimes with the quadratic formula, we get two answers. If you will notice, what is in our numerator is a 2 times a negative 4.905, which means we're going to have a negative value in our denominator. So if my numerator is positive, which would be, well, if I add 36.63, my overall value in the numerator would be positive. I would divide by a negative. A positive divided by a negative is going to give me an overall negative for my result, which I don't want. So I'm probably not going to do this. You can plug it in and try it, but it's probably not going to work for us because we'll get a positive divided by a negative. Which means here, we want our numerator to be negative because we're going to divide our denominator with a negative value. So I'm going to take negative 19.01 minus 36.63, and that's going to give me negative 55.64. So something that looks like this. And then in my denominator, 2 times negative 4.905 is going to give me negative 9.81. And now we'll just divide this. 55.64 divided by negative 9.81. We end up getting about 5.67 seconds. Right? Now, why did I say 5.67 seconds? Well, remember, we're not just solving for x here. X is actually a time value. So our time here should be 5.67 seconds. Now, once we have our time value, we can come back to our list of variables. 5.67 seconds. Remember, time is the one variable both directions will share. 5.67 seconds. And now that we know time, we can solve for delta x using equation 2. So we will set up equation 2, which looks like this. Delta x is equal to initial velocity in the x direction times time, plus 1/2 acceleration in the x times t squared. Again, as we've discussed in class, the reason we like equation 2, especially for the x direction, is because all of this part of our equation goes to 0 because of our acceleration in the x direction being 0. 1/2 times 0 times t squared will give us 0, which means all we have to focus on is this smaller portion right in here. So now delta x is equal to initial velocity in the x, which I can't even remember because we've done so much work. 40.8, there we go, meters per second, times time, which was 5.67 seconds. So we can multiply these together, and we get something in the neighborhood of about 200. 231.4 as our delta x, which does seem like a reasonably high value, but remember, we're launching our projectile at about 45 meters per second, which is roughly like 90 miles an hour, so we should get a pretty high value for our delta x. So now we have a way of solving for our delta x by setting up our scenario, drawing a picture, listing out our variables, and working to get our desired answer. Now, as I mentioned before, the quadratic formula is something we don't actually have to do. So what can we do if we don't want to go there? Well, what I could do is, coming back to my variables, let's say we didn't actually solve for time using the quadratic formula. The only other thing we could possibly find would be final velocity in the y direction, because it's the only other thing that's missing we don't know. So we could use this information if we were to come back to solve for v1 in the y direction, assuming we don't know time yet. That would mean we were going to use equation 5 because we don't know time. So that would look like this. v1 squared in the y is equal to v0 in the y squared plus 2a delta y. A in the y, there we go. So v1 in the y squared, which we don't know, we're going to look for here, we'll talk about why that's important, is equal to v0 in the y, which again I've forgotten, 19.01, here we go, meters per second squared, plus 2 times negative 9.81 meters per second squared, times delta y, which is negative 50 meters. I apologize for running out of space there. Again, make sure we keep track of our negatives, that will be important. So now we will multiply through 19.01 squared, gives us 361.38, and this is plus 2 times negative 9.81 times negative 50. We have two negatives there, so we end up getting a positive value of 981. This is still equal to v1 in the y squared. So we add those values together, 38. We will eventually get a value of v1 in the y squared is equal to 1342.38 you might notice if you went through this using the quadratic, some of these numbers look a little bit similar. Now we'll take the square root. We end up getting a value of v1 in the y is equal to 36.63. Now, from here, remember because we've taken the square root, our answer can actually be positive or negative. Which one do we use? Well, if we're launching something and it's coming back down to a target, it's moving downward vertically, what that means is that our velocity in the y direction should be negative because we're traveling in the negative y direction. Down means negative for the y direction. So our actual value that we want to use should be negative 36.63. Now once we have that, we know v1 in the y direction. I would come back to my list of variables and plug it in. Negative 36.63 meters per second. And then we know everything about the y direction except time. So what's the easiest equation to use? Well, equation 1. So now we can come down here. We can say this, v1 in the y direction is equal to v0 in the y direction plus acceleration times time. And we would plug in, well, v1 in the y, which we just found, is negative 36.63, which is equal to our initial velocity, which is 19.01 meters per second, plus negative 9.81 meters per second squared times t. So to get t by itself, we need to move the 19.01 over. So negative 36.63 minus 19.01 gives us a value of negative 55.65. These will cancel out. Which is equal to negative 9.81 times t. And finally, we divide by negative 9.81 on both sides of our equation. Finish this out. We get 5.67 for our time, which is exactly the same time value we found using the quadratic formula. Now again, really the reason I wanted to show us this is so that we could understand we can use the quadratic formula, or we can solve for our final velocity in the y and then work back to get our time. Either one is an appropriate method depending on what you are comfortable with. As long as you demonstrate what you are doing, hey, there's no reason why one equation or one procedure is better than the other. Hey, I'm not going to go through and solve for delta x again because we already know if our time is good, hey, then our delta x is good. So here, for this complex scenario, remember the procedure. Draw a picture, list out our variables, hey, identify what we know and what we don't know, and then begin the process to solve for our final answer. Here, there were a lot of side steps we had to take. We had to find our components of velocity, we had to find our time, and then work all the way to get our final answer, which was delta x. So remember, even though you're asked for a certain answer at the end of the problem, that doesn't mean that's the only thing we will need to solve for along the way. So, hopefully this gives you a good review on what to do for a complex projectile motion problem. If you have any questions, don't hesitate to ask. Good luck.